All right, without any details, here's kind of what I think with factoring. Step 1, GCF. You can write this if you want to. You have it written down somewhere, I guarantee it. Step 2, is it a binomial? If it is, you have one of 3 options. A difference of squares. And just so you know it exists, and I know you saw it last year, I don't think we hit it this year, a difference of cubes also exists. Or the last one, it could be a sum of cubes. This was not on your flow chart because we didn't, oh, it might have been. That was October, I don't recall. All right, what if it's not a binomial? It might be a what for step 3? A trinomial. Now, these rules are stuck with factoring to solve or factoring to simplify. You just set it equal to 0 if you're solving. For this, you may hear this presented in a different order. I always check, is the leading coefficient equal to 1? And that, somebody already said this word. I think it was Abigail. You said shortcut. Okay, if the leading coefficient of a trinomial is 1, pretty good chance that you're going to have a shortcut with it. Not guaranteed, but you might. If it's not 1, I would check realistically for this, a PSQ. Not Paris Saint-Germain, or Germain, if you will. Little football reference. What's PSQ? I'm going to draw one for you with like some stuff. Let's say that I had this is an x squared. So here's an x squared, and here's an x, and here's an x, and I had a 1 here. What shape do you see on the board? Let me draw it. It's a square. It's perfect. This is perfect square. And I don't know why I wrote Q, SQ for square. It should have been PST. Perfect square trinomial. Okay, do you guys remember when we did vertex form with trinomials and you had to add the clever choice of 0 and do all that? You were completing the square to make a perfect square. Okay, if that doesn't work, what's your next step? Starts the G. Group it. You can group it, hopefully, maybe. Not group, but oh yeah, that's it. Group it. Okay, and then this is where it gets kind of nebulous or unclear, a little bit hard to see because it really depends on the situation. I think when we did this before, I said at this point is where I would jump to quadratic formula. Now, maybe. It depends on the problem because before I think quadratic formula, just maybe I think of PQ. Now, for a trinomial, I probably wouldn't try to do a PQ list where factors of the constant over coefficient and then we deal with them and do the synthetic substitution and all that stuff. I might try it here. Anything bigger than 4, so 4 plus nomial. I'm not going to write all these out, but I would check for grouping right off the bat. That'd be the first thing that I check for every time. I'd check to see if grouping works. If grouping doesn't work for a 4 or 5 or 6, however, if that didn't work, I would then for sure try my PQ or rational 0 theorem to check it out. And if this didn't work, we might switch to different methods, which we haven't really talked about in here, but there's other things that exist. Okay, this is a big old list of stuff that started getting built, I imagine, your 8th grade class when you first saw the idea of GCFs, maybe before then. But then everything in here we've hit. Drive me crazy. I can't remember if we looked at these this year or not. Not our point. All of these exist, and my hope is that when I write these all on the board, you guys have some recollection of them. You might not remember it perfectly because it's like riding a bike, but we've done them all. Okay, with that in mind, this thing looks ugly, but it's not. Is there a GCF? I might catch you. I'm going to make a different claim. Somebody will incorrectly say, yes, there is a GCF. What are they going to say it is? X. 1 is correct, just for the record. There is a 1 in front of both of those. That is the GCF. It's just not meaningful. Why isn't X a common factor? There's something fundamentally different about this. Don't write the red one, but fundamentally different compared to this. What operation's happening here? Okay, this is a harder question. What operation's happening here? It's not sine times x, is it? Because sine doesn't exist on its own. Literally, the operation is sine. And it's the operation sign of that argument. Like, they're fundamentally different concepts. Now, I left class yesterday with a squared minus b squared. If we treat it like that, and you can rewrite it, u and v are more common, but let's check it out. Is there a GCF? Okay. Is it a binomial? Okay. Is it a difference between them? Could you conceivably take the square root of both? Or, wording it the other way, are they both squares? Well, what should we use? It's the difference of two squares. That's what I see up here. So, check it out. As our shortcut, remember, all I'm doing is taking the square root of this and the square root of this. This is our shortcut for the difference of squares. Now, it looks uglier because we're doing trig stuff. It's not. It is exactly the same. What's the square root of sine squared? It's sine. So, specifically, it's sine x, right? Now, I'm going to switch back to black because I want you to write these parts down. Okay, back to this. We have sine x. That's blue, but that's close enough. I don't make mistakes. Why would I need an eraser? Hold on, I got a box of them. Cool. Notice, no mistake in that throw. All right, minus, what's the square root of cosine squared? Bet. It's the cosine of x. Now, there's a product that has to get multiplied by. We need the middle terms to fall out, which the only thing that we need to do is change that middle sign. Sine x minus cos x times sine x plus cos x. We done. Now, I didn't check your work. Did you guys do the same thing?
I did something way crazy with that.
So you might have done your funky Chinese way. Did it work?
I didn't use the Chinese method.
Okay, so I say that, but legitimately, it's a Chinese professor that just teaches factoring a different way, and Huggins stumbled across it, and it works. So I don't know the name of the guy, so I call it funky Chinese way. Cool. All right, we done. Is this, that's physics, first of all. Doable, easy, hard? What do you think?
I did like sine over sine. Like I expanded it so it was sine times sine minus cosine times cosine.
Okay.
And then did sine over sine on both of them. And then I did cosine over sine on the other side. And then I just said 1 minus cotangent squared.
That is not true. I don't know exactly where the mistake happened because I didn't write it all down. Don't erase it. I'll come look. I'll find it. Okay. All right. Let's do another one. And we're just checking factoring at this point. Let's do one more here. Let's get crazy. On B, I want you to explain it to the class. I'm going to pick somebody random, so talk with your neighbors. Make sure you can do it. We are going to try and simplify the following. 4 times tan squared theta. So that felt really weird. I'd never say it like that. 4 tan squared theta. Cool. It felt weird, right? Plus the tangent of theta. Minus 3. Cool. I'm going to pause it here. If you're not feeling very confident, what I want you to do is work through this list. When you find the one that you're going to try to use, if you're uncertain of it, check with your neighbors, check with me. I am either going to ask somebody to try to write on the board or ask for you to guide me through this problem here momentarily. Okay, if you're watching this elsewhere, go ahead and pause it now. You will see a detailed solution in 3, 2, 1 direction. So check it out. I am not going to take the time to do it, but do you guys agree that this expression here looks much less scary?
Yeah.
Okay, they're the same. Like Pam holding the picture in the office meme, they're the same thing. Okay, check it out. There's no GCF because I can't think of anything that goes into 4, tangent, and -3. Nothing. It's not a binomial. It is a trinomial with leading coefficients, not 1. I checked for perfect square. Whether you remember how to do it or not, maybe. But if it's not a perfect square, this will work. Even if it is a perfect square, this will work. Even if you have a shortcut and you don't remember how to do the shortcut, this will work. Grouping works. Okay, why did I draw these? And what do I do with those lines, curves? And what's 4 times -3?
Oh, wait, 12.
-12. Okay, Now, I know that they have to add up to a positive 1, because that's the coefficient here. In my head, I think it like this. It could be 12 and negative 1, and I actually do it the other way. I do 1 and 12, and then I would just say, oh, this one needs to be negative. Those don't add up to 1. How about 2 and 6? Do those add up to 1? What about 3 and 4? Oh. Okay. With that in mind, could it also be 4 and negative 3 if you did it this way? Are you sure? What's 4 times negative 3?
Oh, yeah.
Okay. Which of these would you go with? They're the same numbers, but the order doesn't really matter in the end. One of these helps us avoid mistakes.
4 and negative 3.
That's the way that I'm expecting mistakes. It's not the wrong answer, though, because there's something weird that happens. This is the harder one. This is not the one I would go with, but it's one I'm going to go with, and we're going to see why. Okay, 4 and negative 3, right? Okay, so here we go. I use 4 and negative 3 to do what? Okay, so I'm going to replace this 1 tangent theta with these ones. Cool. 4 tan squared theta plus 4 tan theta minus 3 tan theta minus 3. You may not see the mistake yet, and I haven't truly made it, but I'm about to. I haven't done anything wrong yet. Now, when you group it, I want you guys talk with your neighbors. I want to hear it loud as soon as somebody notices it. I'm going to group them, and I want you to tell me the mistake. So should I just move the negative out? But if I move the negative out and then put parentheses, I'd have to remove the negative from the 3 as well. There's an easy way to remedy this. Because if I do this, and I like your idea there, Riley, but if I do this, now when I distribute, I get minus 3 tan theta plus 9. It breaks it, right? So there's an easy way around it. No, you don't. There's an easy way around this. I can't pull just the negative out without having to think about everything else. But what do we do to make this easier? Why did I leave a little space between them? Subtracting a negative 3, or sorry, removing 3 is like adding a negative 3. Now it's the same thing. Okay.
When you bring the 12 down, like the 4 times 3, what is that called?
This is grouping that we're doing here.
That's
This is grouping because we're taking it with 3 terms. We're finding a way to write it with 4 so we can make these 2 groups. Okay, what goes into this one? Or what comes out, either way? A 4 and a tan theta. That's a different purple, I think. What stayed inside? Tan theta plus 1. Nice job, Mickey. Okay, now remember, whatever I take out of this one, the groups that better match. What could I take out of this to give myself tan theta plus 1 inside? And Riley, if you had done it correctly, and you might have, like I kind of hijacked that whole approach, if you had done it and really carefully taken it, you'd still be okay. This is my way to avoid that. Okay, when I take out a negative 3, it leaves behind a tan theta. What? Plus 1. Do they match? There's a factor. But there's 2 factors here. What's the other one? 4 tan theta minus 3. And we have it. My factorization is tan theta plus 1 times 4 tan theta minus 3. Abigail, I was very aggressive in my comment toward you a minute ago. I think your method will work, but you have to be really careful about when you factor it out of just one thing, how does it affect the other parts? Like, it's less direct than this, but I think it will work out if you're really careful. Okay. Factoring is kind of the bane of our existence, it seemed, this year. You hit it really hard in Algebra 1. I assume you hit it really hard in Algebra 2. I don't know that for sure. If you struggle with factoring, please don't hide it and try to fly under the radar. I want you to be successful. We need to be able to do this. Cool. All right. Should we do another factor or should we switch gears a little bit? One more factor? Okay. Should we get real crazy? Just a little crazy? Not a lot? Oh. No, none of these are crazy. All right, that's okay. Let's do one more factoring. And I'm going to try my best to not give you this in your... Oh, no, just kidding. Yes. I thought we were a section. No, this is a good thing, I promise. For me. Here we go. I want you to factor the following. C for cotangent squared, we'll use alpha. Cotangent squared alpha plus, I'm going to throw you a curveball, cosecant alpha minus 1. Cool. I want you to struggle for about the next 90 seconds or
1 minute first.
get through. Cool. 90 seconds is what you get before I start calling on people. There's something different about this one. So the fact that it's cotangent makes it feel a little bit different, but trig function here or there is maybe not a huge deal. If I wanted to do the same thing that we've been kind of hiding behind the scenes, I wouldn't suggest it. But on the previous one, if I had written it, if I let u equal tan theta, then this we were able to write with 4u squared plus u minus 3. And I did it with x before, but I could call it u or v, doesn't matter. Can I do that here? How sure are you, Angel? Probably less now that I've asked that follow-up. Why doesn't it work here? If I pick u as cotangent, like that seems like a natural thought, let's just see what happens. This becomes u squared plus cosecant alpha. It doesn't match, right? Like I can't just plug in the u for both of those terms. So this one is a little bit harder. It looks a lot harder. It's really not. But there's an issue here. I want you guys to write this comment. You don't always have to. Where happened there? That's weird. I should have just erased it, but we're already committed. All right. I want you guys to make the following comment. Variables, which in this case is cotangent of alpha and cosecant of alpha, variables, VAR, don't match. Okay. Now I'm going to be caveman. We want. And more than want, we need match. So we have a little tiny bit more legwork to do to rewrite it so that we can think about it like we do these regular old trinomials. Now, off the top of your head or off the left side of your trig cheat sheet that should be out for everybody just for the record, I have a choice. I can either try to make it so that cosecant can be written with cotangent, or maybe there's a way that cotangent squared can be rewritten to include a cosecant. Oh my, who? Pythagoras. I want these to match, Kalisha. It's like if I asked you to factor x squared plus y. Minus 1, you couldn't because these don't match, right? So we need them to match. Now, your options are we can either try to write a cosecant, somehow with cotangent included in it, or we can try to write a cotangent squared with a cosecant. Anytime you see trig function squared, what theorems? The Pythagorean theorems. Every single time it should be your first thought. Now, check it out. I don't have the cheat sheet in front of me, and I'm not lying with this. I never remember any of them except for the first one. What's the one free Pythagorean theorem that I do memorize? Sine squared plus cos squared is 1. Okay, as I look at this, and I know you guys have it on your cheat sheets, but I want you to be able to do it without them as well, because if you don't have to look every time, it saves you a ton of time. If I wanted to get a cotangent, is that sine over cosine or cosine over sine? Cotangent is cosine over sine, x over y. Now, what would I need to divide everything by to get cosine over sine? If I divide everything by sine squared, daggone, that's there, and this is here, right? Now, let's just expand one more step. What's cosine squared over sine squared? Cotangent what? Squared. What's 1 over sine squared? Squared. And then this is actually 1, right? So that's my bad. What else do I have to do? I now have 1 plus cotangent squared. Could I just subtract 1? What can I replace my cosecant or my cotangent squared with? 800 numbers calling me. I don't know why. Can I replace cotangent squared with cosecant minus 1? So let's do that. I'm going to use this identity. We're going to replace this with cosecant squared alpha. And I'll do it in 2 steps. Minus 1. And then I'll just keep this other one black. Plus cosecant alpha minus 1. This expression is Pythagorean identity that we just worked out right here. Now, I probably wouldn't have taken the time to put this in parentheses. These parentheses don't really do anything for me right now other than really show where it came from. Can one of the things inside, like if I drop the parentheses, nothing changes. There's no distribution, anything like that. Can I rearrange this one more time? What's the next line going to read? Cosecant squared alpha plus cosecant alpha. One more piece. I think I've just saw two different people say -1. I disagree. -2, right? Because we're just rearranging -1 and -1 as a -2. All right. Once we get here where we have the same variable, now if we wanted to do the let u equal cosecant, could we? This is u squared plus u minus 2, if you want to think about it that way. I don't. I'd rather just write it here right off the bat. Is there a GCF between cosecant squared, cosecant, and 2? Bummer. Is it a binomial? Bummer. Is it a trinomial? What's the leading coefficient? 1. Which means maybe, just maybe, we can use what? The shortcut. Okay. How's the shortcut work? So I'll do it just like I'm grouping it. What's 1 times -2? Okay, can you guys find numbers that multiply to be -2 but add up to +1? -1 and 2 will do the trick. Cool. Now, the fact that this is a 1 right here, and only the fact that this is a 1 means there's a shortcut. If you don't remember the shortcut, could you group it? 100%. You would replace this cosecant with negative cosecant alpha plus 2 cosecant alpha. Now, I would advocate and encourage, the shortcut exists, let's use it. All I need to do, if I'm using this shortcut, is I'm going to take this term, I'm going to take the square root. I know it's cosecant alpha. What's one of the two magic numbers that we just found? -1. Cosecant alpha, what's the other magic number? +2. We're done. Now, I'm going to just move this down a skosh because I don't love the idea of somebody not really understanding this and just going, oh, there's a shortcut, I don't know why it works, but we'll use it. I just want to show you, if you don't know the shortcut and understand why it works, that's okay. We can fix it. Cosecant squared alpha minus cosecant alpha. That's the -1, right? Cool. Plus 2 cosecant alpha minus 2. And I don't normally do this, but I am going to make it 2 distinct steps, and we're just going to get rid of that part. Okay. I take this to the next line. Hey, that fits really nicely in there, even though they're different things. Cool. All right. I take it to the next line, and now I add my group. And just notice what happens. What comes out of the first group? A cosecant. And if I were to factor out a cosecant here, what would it leave inside of this group? Cosecant alpha minus a 1. And what would I take out of this one? Oops. 2, and it leaves behind a cosecant alpha minus 1 again, right? Notice, cosecant alpha minus 1, ta-da. Cosecant alpha plus 2, ta-da. They're there. The shortcut is grouping, but it just always works out this way with leading coefficients 1. Every time. Okay. Everybody's kind of rusty with factoring, huh? Seems that way. Okay. Well, that's all right. We'll get a lot of practice this chapter. It's pretty much all examples at this point. I think I probably made that comment yesterday. Are you guys good at adding? Can you add? If you want to add 2 fractions, they have to, what special? Common denominator. Okay, well, let's just do another example. Let's call this adding. That's it. We're just going to add. Piece of cake. Now, looking at this thing, gosh, there's some cool problems in here. This stuff is so awesome. I want us to do a quick addition. And I'm going to pick one that's not that exact one, and we're going to start somewhere else. I want us to try this one. Yep, cool. Example, I just want us to add. That's it. I want us to take the tangent of x, and I'm actually going to subtract, but it's the same as adding. I want to subtract from this secant squared x over tangent x. Now, I want to stress that it's hard to get the true motivation out of these because we're not, like, I'm just giving you these random expressions and asking you to simplify it. We're not doing the data collection to see where these things naturally show up because all of these do show up in data. There's a reason people study them. Okay, looking at this, we have a bunch of options. This looks kind of hard. I get it. This problem looks easier. Are they different, though? No, they're the exact same. Now, there's two options that I see that I would possibly take. Talk with your neighbors. You're going to need to do some rewriting, which, again, I want to stress, you guys need the trig cheat sheets out. You're going to have to do some rewriting. I need a common denominator one way or the other. I'm going to give you guys 2 minutes to try something. I'm going to come around and eavesdrop and ask you what you're trying and be really mean. Because that's just my nature. Cool. When I look at this problem, I thought the same first thought that Kalisha did, which, cool. If we want to add these, we could just make a common denominator. So what Kalisha did right off the bat was looked at this and said, hey, I want this to be over tangent, which, because I don't have an equal sign, it's not like I can multiply both sides, but what can I multiply by? Tan over tan, right? That's just a clever choice of what number? So you're about to see my notation, and I'm going to leave the arguments off just because I'm out of room. If I do this, I think the next thing that I get is, in the numerator, it's tangent squared x over tangent x minus secant squared x over tangent x. Everybody okay with what I've done? It is not the only option, and I want to stress that because I saw 3 options that work in here. This is the one that I would go with first in my head. Now, do they have a common denominator at this point? Do I really need to write 2 different fractions in? So I'm just going to shove them together then. The numerator becomes what? Tan squared x. I'm getting whispers. I think it's that. All divided by tangent. Okay, again, I can't believe that I don't have these memorized because of how many years I've taught this and I use them. They just don't stick. That feels and looks to me like it is going to be an identity. Pretty sure of it. I'm going to check it real quick. Sine squared plus cos squared is what? A 1. So let's see if I need a tangent, because I have a tangent here, that's what I'm thinking. I'm going to divide everything by cosine squared. And what I recognize is tan squared plus 1 equals secant squared. Okay, that's one of your Pythagorean identities. Guarantee it. Now, this thing has a tan squared minus secant squared. Could you rearrange this to make it look like that? So more specifically, help me rearrange this. I want this to look like this numerator. 2 steps, I'm going to do it in 1 line. I'm going to subtract a 1 from each side and a secant squared. A -1 though. Everybody on board with what I'm doing here? Like, it might not be the same way you did it, but that's okay. What can I replace the numerator with then? It's a -1. Well, that's okay, but I could make it nicer. What's 1 over tangent? So this is just negative cotangent x. I'm going to go over here to do it. Now, in this problem, it takes practice, which, I mean, that's why we're here, right? It takes practice with these things to get used to it and to just feel comfortable stepping out into something that you don't know. Again, I made this comment earlier. Welcome to life. It's going to happen over and over, whether it's in this classroom or like elsewhere. You're going to go into something without knowing the real way through. Every adult does that every day. It just looks like we know what we're doing. Okay, this is not the only way. Somebody else changed to sines and cosines. It gets ugly because you have to play the fraction game so hard, but it works. I probably would not do that one. There is one other thought that I have that somebody, I think it was Bea that did it. When I start this expression right from the get-go, and I guess before moving on to a different route, the way that I just worked it, were you able to follow? Could you replicate it if you needed to? I bet we find out because that's how class typically works. Okay, in contrast with this, the other thought that I have initially looking at it, and if you want to write down multiple approaches, you can. If you just want to follow along, as long as you're thinking about it, I'm good with it. The other thought that I have when I look at this is, right off the bat, I notice there's a trig function squared. I really wish I hadn't just erased my Pythagorean theorem. What's the trig function or the identity that has secant squared? I'm going to look at your sheet. So if I wanted just secant squared, it's 1 plus tangent squared, right? So in my head, and I don't know if this is going to work nicely, but the next obvious choice would be to do this. 1 plus tangent squared over tan x. Before I move forward, can you guys convince me that I'm allowed to do this? Let me rephrase that. Talk with your neighbors. I'm going to call in one random person. Convince me that I'm okay to do this. Why did I just make that change? Do you see which way I chose to get that? Anytime, and if, like, you might know, I just give you time, that's my bad. Anytime you see something square, your brain should always go here because it might work. Every single time. So as soon as I see secant squared,
You know,
I know it's 1. It's actually 1, yeah, 1 plus tangent squared. So that's all I know. Okay, now it doesn't look that nice yet, does it, or doesn't? I can't tell. What do you think? Does this look like it's going to shake out real nice? Well, let's try it, because now I just made the fraction uglier, which seems like counterintuitive and maybe against what we're trying to do. But maybe we didn't. I still need a common denominator, yeah? I'm going to multiply this by tangent over tangent, my clever choice of 1 again. And then I would have tan squared over tan. But I'm just going to shove it all together like I did here. So I get tan squared x minus, I'm going to distribute, 1 minus tan squared x, because I just distributed this. And it's still all over what? Tan x. Now I skipped a step of work because it's shown on this other left side. Anything convenient happen? Chapa, chapa. And we're left with negative 1 over tangent x, which is, it's negative cotangent x. You find an identity and you plug it in, pretty good chance it will work for you. Like every time. Be comfortable taking the step, just like with proof stuff. Okay. We should do another one like this probably. Cool. Ooh boy. All right, we're going to take a step away from the trig for a second, just real temporarily. Is this really hard stuff? I can never get a read. JV, scale of 1 to 10, where 10 is like, oh my gosh, this is so awful. Where would you put it? 10's the hardest stuff you've ever done. So not too bad. Okay. Without calling anybody out, somebody I imagine is looking at 8 or 9s here, just because it looks so ugly. I'm going to throw you one tiny different one. I want you to try to do the following for me, and I got to try to think this out. This is B, right? Okay. There's no trig in this one. I want 1 over 1 plus A. And I want you to add this to 1 over 1 minus A. No trig. I want you to show me it's kind of gross, but show me the common denominator stuff, deal with these fractions. I'm going to give you a little bit of time. As we look at example B, if you want to add those, they have to have a what? Common denominator. Now, it's convenient if it's the smallest, but it doesn't have to be, right? Like, they just have to be common. Right now, there's no parentheses, but if you want to think about it as there's like this whole thing in the denominator, I see this has a 1 plus A, and this one has a 1 minus A, right? This one needs a 1 minus A, and this one would have to have a 1 plus A added to it. So, this is going to look ugly for a second. I'm going to sneak it in here. Am I allowed to multiply by this if I want? Okay, that makes my denominator 1 minus a, 1 plus a. What do I have to multiply this one by to do the same thing? Let's just multiply by the other denominator. 1 plus a over 1 plus a. And let's just see where this shakes out. Now, in the denominator, because it's all added together, I would encourage just go one step. The denominator right now is this ugly mess of a thing. 1 plus a over 1 minus a. Okay, what about the numerator? This one becomes 1 minus a, right? Plus, what's this one become? 1 plus a. And done, done. And it looks like this thing simplifies as far as I can go. 2 over 1 plus a times 1 minus a. Now, if you're feeling super adventurous, there's one more step the algebra could take us to. Anybody tell me the last thing that algebra is just saying, please do that? To do the distribution downstairs. And it feels weird to do it, and I'm going to be honest, in a normal problem, I would never do this. But we're not doing just normal problems. This becomes 1 minus a squared. This is what it winds up being. Okay. This may, like, we're knocking the rust off because, jeez, I almost rolled my ankle. That was weird. We're knocking the rust off. It's been a while since we've done this. But can you guys follow along here? Okay. Can you tell that in parallel why I've chosen to do this prior to this? This problem might not seem super easy, but it's likely not the worst thing you've ever done. This problem's the same. Identical. This has a 1 plus sign. What does it need? A 1 minus sign. So I want you guys to knock this one out. Just draw the line there. This needs a 1 minus sign downstairs and a 1 minus sign upstairs, because the only thing I'm allowed to multiply by is what? 1. And I'll add the theta to make sure it's there. This one has a 1 minus sign. What does it need? 1 plus. I want you guys to do the exact same thing that we did here. We're just going to replace a with sine theta. Now, don't just cheat ahead and say, oh, well, I'll just plug in sine theta for this. Verify that you can do the work. And I'm going to say dot, 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 because I'm going to let you do it. We should come to a point, and if you get anything other than this, let me know. You should get to a point where we wind up with this. Don't just jump right to it. Make sure you understand the math that's building up to that. There's even one more step behind you. Who was better than fractions? Not fractions would be nicer, right? If only that could be changed into something. Cool. I'll give it about 20 more seconds and we'll kick through the rest of this. Yeah, there are so many cool problems in this section. Okay. Once we get here, our problems are going to start to look a little... Ugh, that was weird. Start to look a little bit different. I have something sticking in my throat. I see something in there that's just screaming, no, yep, the door's closed. Identity! What's screaming identity up here? Holy Pythagoras. 1 minus sine squared is cosine squared. Which means we're one step away. We're going further than we did with the algebra because we're in trig land. 1 minus sine squared is cosine squared. This is pretty nice. This is a much nicer expression to start with or to deal with than one over, like this beginning mess. But I asked Abigail this question a second ago. Now it's your turn. What's better than a fraction? Not a fraction. Now, 2 over cosine is something. That's 2 times 1 over cosine. It's squared, but what's 1 over cosine? And if you did 1 over cosine squared, it'd just be secant squared. Now we have a singular expression resulting from all of this algebra just being applied to the trig. Cool. They look new, they feel new. There's one extra step than you've done before, but there's nothing on here that you haven't seen. We did this year as well with the partial fraction decompositions is what it makes me think of. We've done these. We're doing the same thing you've done this year, probably a little bit of last year. I'm trying to decide. You guys have a lot going on this weekend, but I'm also not here next week, so I want to make sure I'm here Monday. We're gonna, what's up? I'm here all of Monday. I fly out Tuesday with the basketball team, I think. So you guys get to watch me cry if we get turbulence. I'm not kidding. All right. You guys are gonna get a short assignment over the weekend. Okay. We're gonna make a deal, and I'm gonna trust your judgment because I'm not hurt if your judgment is not true. I want you to do at least 4, but I would encourage you, I think you should do all of them. But homework, we'll call this 5.1.1. You'll find this on page 355. I want you guys to do, oh my gosh, they're all so good. At least 4, but you should do all of them, 21 through 28. Bare minimum, if you get through 4 of them and you go, I'm good, I'm going to trust your judgment, but it's not my quiz score that's at risk here. At least 4 of these, you may as well just do all 9 of them, realistically. But I'm going to trust your judgment. Cool. We will check this Monday. You're the one class that I guarantee gets videos. I will record 4 videos for next week for you guys, because I'm not going to make you read the book for it. Cool. All right. If you have questions, if you can't get through 4 of them, when should you come see me? So I'd prefer Monday before school, since we're going to check this Monday 4th hour. If you start working this Sunday when you have a little bit of downtime and you realize you can't do any of them, please come see me Monday morning. I will help a lot. All right. Later, Raiders.
Yeah.